A note on the page of an old Russian calendar recorded the fall of a meteorite in the vicinity of the Siberian town of Kansk in 1908. The note attracted the attention of Soviet scientist L.A. Kulik, who specialized in the investigation of meteorites. Kulik came across the note in 1921 as he was arranging a meteorite expedition. Even though meteorite research by the Academy of Sciences of the young Soviet Republic was necessarily limited, Kulik had interested 3 other members of the Academy, Vernadsky, Versman, and Oldenburg, to join him on the expedition to Siberia. In the fall of 1921, the first Russian expedition on meteorites left Petrograd for Siberia. The investigators soon discovered that the meteorite which had been observed near Kansk did not fall in the Kansk region. Records in other towns in central Siberia also noted the appearance of an unusual phenomenon on June 30th, 1908, a phenomenon that was observed and heard by thousands of people throughout the huge territory of Siberia. Eyewitnesses told of a blinding flash of light over the taiga and a powerful gust of air, indications of a highly unusual cosmic event. Kulik attempted to pinpoint the location of the suspected meteorite fall in the area of the river Podkamenia Tunguska, and his preliminary investigations suggested an event of significance to scientists throughout the world. While they failed to locate the mysterious Tunguska meteorite, Kulik's expedition did not return to Petrograd empty-handed. 233 meteorite samples were added to the collection of meteorites of the Academy of Sciences and were placed on display in Moscow. Kulik's efforts to organize another expedition were strongly supported by his Siberian scientific colleagues. Geophysicist Voznesensky, who was in charge of the observatory in Irkutsk, reported that the seismograph in the observatory registered a strange and prolonged disturbance during the night of June 30th, 1908. Comparing his findings with the observations of others, Voznesensky established that the time of the disturbance corresponded to the fall of the Tunguska meteorite. The first hump corresponds to the beginning of the seismic wave, followed 48 minutes later by the air pressure wave. The interpretation of the seismographic data and the observations of the witnesses helped pinpoint the area of the fall. According to Voznesensky, the flight of the meteorite was in the direction of south-southwest to north-northeast. His observation agreed with the findings of a young Siberian geologist, S. Obruk, and the Siberian ethnographer I.M. Suslov, who had been in the Tunguska River area at the time. These findings renewed Kulik's determination to find the Tunguska meteorite and provided the justification he needed to begin preparations for a new expedition. The trading post at Vanovar became the base for Kulik's new expedition. The Siberian trading posts were of major economic and cultural importance to the inhabitants of these remote areas. Workers at Vanovar helped Kulik organize the expedition and participated in finding experienced guides. Kulik is shown at the left in this group photograph. In 1928, he decided to lead the expedition through the waterways upstream into the remote taiga, where he hoped to find the Tunguska meteorite. Thorough preparations were made for the expedition. Special boats were built for the trip, utilizing techniques commonly employed in that area. The boats are exceptionally well suited for Siberia's turbulent rivers. Preparations completed, the expedition was ready to travel as soon as the river was free of ice in the spring. Kulik's party traveled 16 days, crossing the river many times, cutting through timber, and carrying their equipment when necessary. For 16 days, they fought the elements, every day knowing that they were coming closer and closer to their destination. When they had gone as far as they could by boat, Kulik established his camp on the bank of the river Kushmo. A charcoal pit provided an acceptable substitute for a baking oven. Truly fisherman's luck. After hiking tens of kilometers and frequently chopping through the woods, the expedition reached its destination. Trees lying radially in the form of a huge circle still mark the site some 20 years after the event. The impact must have taken place in the center of that circle in an area of great swamps. Kulik felt that the depressions in the swamp were craters formed by meteorite fragments. Now, all his energy was directed toward finding and retrieving remnants of the meteorite. First, a topographic map of a 100 square kilometer area was prepared. Then, an attempt was made to dry up one of the craters. And an excavation was started. However, the expected meteorites were not recovered. The results of the following year were no different, even though the search was very thorough. In addition to excavations, drillings were performed. Also participating in the expedition were the botanist Chumilova and a young astronomer named Krinov, who conducted astronomical observations. After 3 years of searching, Kulik became discouraged. He had not found a single gram of material of meteoritic origin. All this cast doubt on the usefulness of future trips into the area. Meanwhile, some British scientists had become interested in Kulik's investigations. In London, Dr. Scholl recalled a recording made from a microbarometer in 1908 indicating a disturbance of unknown origin. He noted the possibility that the microbarometer reading was related to the fall of the Tunguska meteorite. The English scientist Whipple then calculated the speed of the pressure waves and the energy of the Tunguska meteorite explosion on the basis of microbarograms. During this period, Vernadsky, who had been a member of the 1921 expedition, attentively followed the investigations of the Tunguska meteorite. He hypothesized that it was possible the Tunguska meteorite actually resulted from the penetration of a huge mass of cosmic dust into the Earth's gravitation field and was a comet-like body rather than a true meteorite. His assumption was supported by the Soviet scientist Ostapovich, who had collected and published eyewitness accounts from various areas of Siberia. This map illustrates the points where the flight of the meteorite was observed. The points where the earthquake was observed, and locations where thunder and noise were heard. All these occurrences covered an area of over 1 million square kilometers. Ostapovich then calculated the direction of flight of the meteorite, and later his determinations were refined by Krinov. The explosion took place at 016 minutes Greenwich time. The air pressure wave was registered by numerous meteorological stations in Siberia. It traveled with the speed of sound and was recorded in Leningrad, Copenhagen, Potsdam, Zagreb, and London. The airwave traveled twice around the world and converged in the Drake Strait between Antarctica and South America. Its energy was 10 to 21 ergs. Kulik, however, never gave up hope that one day he might find a fragment of the Tunguska meteorite. He continued collecting other meteorites and studying the conditions of their fall as he searched for clues to help him in further investigations of the Tunguska meteorite, fragments of which he assumed were still hidden in the swamps. Technological advances made aerial photographs available for further investigations, and in 1938, Kulik continued this work with the help of Schmidt. He finally obtained 1,500 photographs for use in studying the area. From these, he confirmed the uprooting and destruction of the forest. He then initiated a new program of activity. He outlined a comprehensive investigation to be completed by 1943, but his work was interrupted by World War II. Kulik, along with thousands of other Soviet citizens, volunteered for the front. He did not return. Shortly after the war, the attention of Soviet astronomers was attracted by another spectacular occurrence. On the 12th of February in 1947, a huge meteorite fell in the region of the Kotalin Range. The Academy of Sciences organized an expedition into this area under the direction of Fezenkov. When the scientists approached the area, they saw a scene similar to that which Kulik had seen on arrival at Tunguska. Before them lay hundreds of small craters formed by the impact of meteorite fragments that had disintegrated in the air. This was an iron meteorite, and the magnetometric method was employed for investigation and recovery. The meteorite fragments had penetrated the soft ground and were found as deep as 8 meters or more than 26 feet below the surface. This sizable fragment weighed 350 kilograms. And the larger one weighed 700 kilograms or 1,540 pounds. Approximately 23 tons of meteoritic material were collected from this site in the Kotalin Range. In the north portion of the meteorite field, some individual meteorites were found in craters formed from the breakup of the parent body during its flight through the atmosphere. The molten metals solidified on the surface of the meteorite, forming streaks and small spherules. This type of spherule was also found in the soil. The investigators remembered that Kulik had also found silver-gray spherules in the soil samples of Tunguska. Investigation of the soil samples Kulik collected was repeated, and Yafnel found magnetic particles in the samples. The foundation for understanding the nature of the Tunguska meteorite occurrence was developed on the basis of experience obtained during this study of Sikhote-Alin. Basic theories of meteorite impact were also developed through this research. Bezenkov calculated the mass of the meteorite as over 1 million tons. This was done on the basis of its trajectory, orbit, and the observed murkiness of the weather in California in 1908, as reported by Charles Greeley Abbott and published by the Smithsonian Institution. Bezenkov hypothesized that these weather observations were related to the disintegration of the meteorite. All these occurrences were studied and analyzed by Krinov, a co-worker of Kulik. His monographs and publications served as the basis for further fieldwork. The geochemist Florensky was in the Tunguska area in 1953 and suggested that further field investigations of Tunguska should be undertaken. Yafnel's discovery of metallic spherules in the soil samples which Kulik had obtained from the Tunguska area became the decisive factor in planning a new expedition. By 1958, 30 years had passed since Kulik's first expedition. The original trading post had changed and was now the main center of the Vanovar district. In the main street, an astronomical benchmark placed by the expedition in 1929 still stands. The 1958 expedition set forth on the same route which Kulik had taken earlier. The trail which Kulik's expedition had cut through the taiga was unrecognizable. The trail was covered with underbrush. However, the huts were rather well preserved, as was the meteorological station. The scene had changed somewhat since Kulik's first expedition, though reminders of his work were still in evidence. The great swamp continued to guard its secret. However, after 30 years, science and technology had changed considerably. The main purpose of Kulik's trip had been to locate huge meteoritic masses, but now the purpose was to find very small particles of cosmic dust. Magnetic methods were used to collect sample material. All samples were sent to the camp, which was again based on the river Kushmo. In samples taken from the central portion of the uprooted area, metallic and silicate spherules were found. The spherules were subjected to investigation in a field laboratory, and the chemical elements normally present in cosmic substances were found in these spherules. It was noted that the number of spherules in the soil increased with distance from the center of the area. With these findings, it became necessary to increase the area of investigation. Sampling procedures employed while moving through these remote areas required ingenuity. The expedition carefully documented all areas where the forest was destroyed, more precisely determining the boundaries of the area where the forest had been uprooted. Land contours were measured, as was the direction of uprooting of the trees. As a result of this investigation, the first schematic chart of the uprooted forest was prepared based on a thorough topographic study. The chart was completed in 1961 with a detailed description of the taiga. The area covered 2,000 square kilometers. The expedition in 1961 was the most productive of all the expeditions to the Tunguska area. It comprised a large group of scientists of various disciplines. An independent biological expedition had joined the fieldwork in 1960. At that time, 120 stations were set up, which served as the basis for detailed studies of the direction of the uprooting. The director of this group was an engineer by the name of Plekhanov. His group also noted the rapid growth of trees following the year 1908 and the nature of their scorching. There was a general notion among the people that the Tunguska meteorite must have been the result of a nuclear explosion of a spaceship. However, the enthusiastic young investigators corrected this notion. They cut down trees and investigated the rings, tracing them to the year 1908. The ash was then subjected to radiochemical investigations, and no traces of radioactivity were found. At the same time, another group was conducting an investigation in the area of the swamps. The magnometric method was employed, as during the earlier investigation of Sikhote-Alin. However, conditions under which they were to work were frequently much more difficult. Masses of magnetic material could not be found on the bottom of the swamps, and specialists came to the conclusion that the depressions in the swamp and the layers of peat were of terrestrial origin and had no connection with the fall of the meteorite. It soon became evident that the cosmic body had exploded in the air and did not reach the Earth. This lake, which is sometimes called Swan Lake, is the largest body of water in the vicinity of the fall. From the sediments of such a lake, Similarly, as with the rings of a tree, one can study yearly deposits. Now, with greater effort, the search for meteoritic material continued. The scientists were able to establish the aerial distribution of the concentration of magnetic spherules. It led in a northwesterly direction, and it was explored for a distance of 400 miles. In 1962, the work of the expedition was transferred to the banks of the river Chunya. Samples from the bottom of the lake were also studied. From various points, samples were delivered by helicopters to the base camps. The initial investigation was performed in a field laboratory. However, the basic work was performed in Moscow in the Vernadsky Institute of Geochemistry and Analytical Chemistry. Various instruments were employed to separate the magnetic portion from the bulk sample. And the sample was separated into size fractions. The magnetic drum collects the magnetic portions from the bulk sample. From this vibrating flat surface, the scientifically important spherules were obtained. Spherules 1/100th of a millimeter in size were subjected to special chemical analyses. For this type of analysis, unique techniques were employed. This balance can be used for weighing 1/1000th of a gram. Micromanipulators place the spherule into a container of minute diameter. A sample is obtained by use of a centrifuge. The separated density fraction can only be worked with under a microscope. X-ray spectroscopic investigations were also conducted, along with the microchemical work. This method allows the study of chemical composition of various points within a dust particle. The analysis indicated that nickel was not distributed evenly within the spherules. Its composition varied distinctly from the center to the outside of the spherule. What was the cause of such a significant difference in the distribution of the nickel? Could it be connected with the origin of the spherules? An experiment was performed in an attempt to find the answers. Minerals characteristic of cosmic bodies were investigated in Florensky's laboratory. Tiny grains were melted, gases evolved, and complex chemical processes took place. Finally, artificial spherules were obtained. Analyses of these spherules produced the same results found earlier in analyzing the natural material. This agreement substantiated the theory of cosmic origin of the collected spherules. The study of the Tunguska Fall is a part of the broader problem of the interaction of cosmic matter with our planet. This area of study in the USSR is directed by Vinogradov, a member of the Soviet Academy of Sciences. The work related to the fall of the Tunguska meteorite is complex and has been conducted in numerous scientific institutions. Kulik's map, based on aerial photographs, was refined. This map served as a basis for an experiment which simulated the destruction of the forest. The forest was represented by wooden sticks supported by soft wire. An explosive charge was set off above the simulated forest. The charge represented disruption of the meteorite, and the resulting air blast reproduced the pattern of destruction observed in the field. The destruction of the forest caused by the ballistic wave follows this pattern. The center of the impact area, without uprooting of trees and destruction of the forest, is duplicated just as it was observed at Tunguska. On the basis of these objective experiments, the trajectory of the meteorite and its energy were calculated. The tree samples obtained from the Tunguska area were studied in the Botanical Garden of the Academy of Sciences. Experiments were performed which simulated scorching due to flash heating. Comparisons of the scorched trees in the Botanical Garden with samples collected in the field showed significant similarities. Here are pictures depicting the night of June 30th in 1908 in England, Denmark, and Russia. The night was very bright. The boundaries of this occurrence were determined by the Committee on Meteorites of the Academy of Sciences of the USSR. The area spread over the northern hemisphere west of Tunguska. Bezenkov declared that the Tunguska meteorite was actually a comet and cited the following occurrences as proof of its cometary nature: the destruction of the forest, the unusually strong pressure wave, the absence of large masses of meteorite material, the presence of silicate and nickel-iron spherules, and finally, the nature of the orbit of the cosmic body. Without any doubt, this was a comet. The approach to the Earth of comets from the distant cosmos is well understood. Comets consist of gases and small particles moving under the influence of solar radiation. A number of instances of comets approaching the Earth have been recorded. The approach of the Tunguska comet was not observed because it approached the Earth from the direction of the sun during the daytime. The tail of the comet, composed of cosmic dust, was caught at a height of 600 to 800 kilometers above the Earth in the northern hemisphere, and there it created an unusually bright night. The head of the comet approached with cosmic speed, and upon entering the Earth's atmosphere, disintegrated into small particles, forming a shock wave. At a height of 10 kilometers, the remaining mass exploded, completely disintegrated, and particles were carried by winds far to the northwest. This was the sequence of events that led to the Tunguska phenomenon, which occurred half a century ago. While meteorite craters are preserved on the surface of the Earth for tens of thousands of years, the traces of atmospheric explosions are covered quickly by vegetation. And if the Tunguska fall can be considered a meeting of a comet and the Earth, then we can assume that such occurrences have happened previously. Kulik's persistent search for the Tunguska meteorite resulted in a more profound discovery than was originally anticipated and helped increase man's knowledge of the universe.